Here's a puzzle that seems deceptively simple, but has been used to challenge job candidates at major tech companies and even appeared in mathematical olympiads. It's the kind of problem that makes you think you've got it figured out, until you realize you're barely scratching the surface. You have 8 batteries and a flashlight. Due to a manufacturing defect, exactly 4 of these batteries are good and functional, while the other 4 are completely dead and won't work at all. The good and bad batteries look absolutely identical. They've been mixed up, and you have no way to tell them apart just by looking. Your flashlight has a simple rule. It will only turn on if you insert exactly 2 good batteries. If you have 1 good and 1 bad battery, nothing happens. If you have 2 bad batteries, still nothing. Only 2 good batteries will make that flashlight shine. The challenge? What's the minimum number of tests needed to guarantee, in the worst-case scenario, that you can identify 2 good batteries and get that flashlight working? Before you dive into the solution, pause for a moment. Your first instinct might be something like, well, I'll just test them one by one until I find what works. But how exactly would you do that systematically? And more importantly, how do you prove that your method is truly optimal? Let's number our batteries 1 through 8 and see where this leads us. We'll start with testing battery 1 against batteries 2, 3, 4, 5, 6, 7, and 8. That's 7 tests. If the flashlight stays off in all cases, we can definitively conclude that battery 1 is bad. Why? Because we know some of the other batteries must be good. So if 1 paired with all of them produces nothing, then 1 must be the problem. Now we test battery 2 against the remaining untested combinations 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, and 2, 8. We already tested 1, 2, so we skip that. That's 6 more tests. If all fail, battery 2 is bad. Following the same logic, we test 3, 4, 3, 5, 3, 6, 3, 7, and 3, 8. That's 5 tests. If all fail, battery 3 is bad. We test 4, 5, 4, 6, 4, 7, and 4, 8. That's 4 tests. If all fail, battery 4 is bad. At this point, we've identified 4 bad batteries through systematic elimination. The remaining batteries, 5, 6, 7, 8, must all be good. So we perform one final test with any 2 of them, and the flashlight turns on. Total tests: 7 plus 6 plus 5 plus 4 plus 1 equals 23 tests. This method works, but 23 tests feels excessive. Surely we can do better than this mathematical sledgehammer approach? Strategy 1. Here's where strategic thinking begins to pay off. Instead of testing batteries individually, let's test them in pairs from the start. We test 4 pairs: 1, 2, 3, 4, 5, 6, and 7, 8. That's 4 tests. Now, here's the key insight. Suppose the flashlight stays off in all 4 tests. What can we conclude? If the flashlight is off, each pair must contain at least 1 bad battery. Since we have exactly 4 bad batteries in total, and we need at least 1 bad battery per pair across 4 pairs. If any pair had 2 bad batteries, we wouldn't have enough bad batteries left for the other pairs. So, each pair has exactly 1 good battery and 1 bad battery. Now comes the clever part. We take 2 pairs and test all possible cross combinations. Let's test pair 1, 2 against pair 3, 4. Test 1, 3. Test 1, 4. Test a 2, 3. Test a 2, 4. Since each pair has 1 good and 1 bad battery, exactly 1 of these 4 tests will turn on the flashlight. Specifically, when we pair the good battery from the first pair with the good battery from the second pair. Total tests: 4, initial pairing, plus 4, cross pairing, equals 8 tests. This is a dramatic improvement from 23 tests. But wait, there's more than one way to achieve this result. Strategy 2. It's an entirely different approach that also achieves 8 tests. Start with dividing the 8 batteries into 2 groups of 4. Group A, batteries 1, 2, 3, 4. Group B, batteries 5, 6, 7, 8. In Group A, test every possible pair combination: 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. That's 6 tests total. If the flashlight stays off in all cases, what does this tell us? If all pairs in a group of 4 batteries fail to turn on the flashlight, then at most 1 battery in that group can be good. Why? Because if 2 or more batteries were good, at least 1 of our pair tests would have succeeded. If all 4 batteries in Group A are bad, then all 4 batteries in Group B must be good. We simply test any pair from Group B, and the flashlight turns on. Total tests: 6 plus 1 equals 7. If exactly 1 battery in Group A is good, then Group B has exactly 3 good batteries and 1 bad battery. We test 2 different pairs from Group B, say 5, 6, and 7, 8. At least 1 pair will turn on the flashlight. Total tests: 6 plus 2 equals 8. Maximum tests needed, 8 tests. Both strategies achieve 8 tests, but through completely different logical pathways. This hints at a deeper mathematical structure, but it also raises the question, can we do even better? Here comes the truly elegant solution, one that achieves the theoretical minimum through a stroke of combinatorial genius. Divide the 8 batteries into 3 groups. Group 1, batteries 1, 2, 3. Group 2, batteries 4, 5, 6. Group 3, batteries 7, 8. In Group 1, test all pairs. 1, 2, 1, 3, 2, 3, 3 tests. In Group 2, test all pairs. 4, 5, 4, 6, 5, 6, 3 tests. In Group 3, test the only pair. 7, 8, 1 test. Suppose all these tests fail. Here's the beautiful logical cascade. If all pairs in a group of 3 batteries fail, then at most one battery in that group can be good. Since we have 2 groups of 3, each can contain at most 1 good battery. That's at most 2 good batteries across both groups. But we know there are exactly 4 good batteries total. Where are the other 2 good batteries? They must be in Group 3, which means both batteries 7 and 8 are good. Test batteries 7 and 8 together. The flashlight turns on. Total tests. 3 plus 3 plus 1 equals 7 tests. Now comes the crucial question that separates a good solution from a great one. Could we possibly do it in fewer than 7 tests? The answer is a definitive no, and here's the elegant proof using graph theory. Represent each battery as a node in a graph. Each test of 2 batteries becomes an edge connecting 2 nodes. Our goal is to ensure that among any 4 nodes representing good batteries, at least one pair is connected by an edge. Assume we can solve the problem with only 6 tests, 6 edges. Suppose nodes 1, 2, and 3 form an independent set, no edges between them. For the remaining nodes, 4, 5, 6, 7, 8, each of these nodes must connect to at least one of 1, 2, 3. Otherwise, we could find 4 nodes with no connections between them, which would mean 4 good batteries that were never tested together, violating our requirement. With 5 nodes, 4 through 8, each needing at least one connection to 1, 2, 3. We need at least 5 edges just for these connections. But now we have only 1 edge remaining out of our 6 total edges. Where can this final edge go? If it connects within 1, 2, 3, then 4, 5, 6, 7, 8 forms an independent set of 5 nodes, meaning we could have 4 good batteries among them that were never tested together. If it connects within 4, 5, 6, 7, 8, we still have at least 4 nodes in this set with no connections between them. The inescapable conclusion: with only 6 tests, we cannot guarantee that we can always identify 2 good batteries. Therefore, 7 tests is the absolute minimum. Here's the summary of the method that achieves the optimal solution. Step 1. Group the batteries 1, 2, 3, 4, 5, 6, 7, 8. Step 2. Test all pairs within each group. Tests 1 through 3, 1, 2, 1, 3, 2, 3. Tests 4 through 6, 4, 5, 4, 6, 5, 6. Test 7, 7, 8. Step 3. Analyze the results. If any test succeeds, you're done. You found 2 good batteries. If all tests fail, then batteries 7 and 8 must both be good, by the elimination logic. Step 4. The final verification test with batteries 7 and 8 confirms your success. Now that you've mastered the 8 battery problem, here's a natural extension to test your understanding. What if you had 12 batteries with exactly 6 good ones, and you needed to find 3 good batteries? How would you modify the strategy, and what would be the minimum number of tests required? The principles you've learned here, strategic grouping, elimination logic, and mathematical proof techniques, will serve as your foundation for tackling this and other similar optimization puzzles.